So if I need to solve Laplace's or Poisson's equation, how do I go about it? The Laplace's or Poisson's equation being a PDE, it is possible to solve it analytically. And when you are able to solve an equation analytically over a solution region, you will get the exact solution. That is the best available option, where you have the exact solution which gives me the field map in the solution region. So what I'm going to do here is I'm going to show you an example problem that has been solved in Sadhiku's book of electromagnetics. This is page 205. A photocopying machine uses the principle of electrostatics. What you have is, in a photocopying machine, you have a photoconductor. This photoconductor is represented by the lower rectangle. And light from the document to be copied is focused on the photoconductor. So there is this, you can see these light rays coming and falling on this photoconductor. When light from the document to be copied is focused on the photoconductor, the charges on the lower surface combine with those on the upper surface. The charges on the lower surface combine with those on the upper surface, and they neutralize each other. So depending upon what you have on the paper, lights will pass through in a particular pattern, and according to the pattern in which light passes through, will decide which of the charges will be neutralized and which will not be neutralized. So the image is developed by pouring a charged black powder over the surface of the photoconductor. And the electric field attracts the charged powder, and this is transferred to the paper and melted to form a permanent image. So this is the basic principle in which a photocopier works. In this particular example, what we would like to do is, we would like to determine the electric field above and below the surface of the photoconductor, of course in an idealized situation. So you have two materials. You have a material with epsilon R1 and you have a material with epsilon 2. Epsilon 2 is the material of the photoconductor and epsilon 1 is air. And you have a potential applied on this. There is some, you don't really have a potential applied, but you have some free surface charge on the interface between epsilon 1 and epsilon 2. The thickness of epsilon 2 is A, and the thickness of the entire two blocks together is D. This is earth, this is earthed. In this scenario, I would like to solve the Laplace's equation analytically to obtain the electric field, the exact solution for the electric field in both the materials. Now, since there is no volume charge density, we will not need to solve Poisson's equation, we only need to solve Laplace's equation. Potential depends only on x because it has symmetry in the y direction, and so this reduces to a one-dimensional problem. So del square v equal to 0 is a Laplace's equation. In one dimension, that is equal to del square v del x square equal to 0. Integrating, I get del v del x is equal to b. Integrated again, we get v is equal to ax plus b. Now, a and b are constants which need to be determined. How do I determine that? From the boundary conditions. I know that v1 is the potential that is applied on material epsilon 1. So that gives me v1 is equal to a1x plus b1 when x is greater than a. And V2 is the potential of the photoconductor material. So V2 is equal to A2x plus B2 when x less than A. If I go back to the previous slide, that means this is V1 in this region and V2 is in the region of epsilon 2. This is the condition that I have. I also know that V1 at x equal to d is equal to 0 and V2 x equal to 0 is equal to 0. So I am basically talking about these grounded plates. At x equal to 1, the two potentials must be equal because you have continuity of potential across interfaces. So therefore, V1 is equal to V2. And I also know that there is a free surface charge density at the interface. So therefore, dn1 minus dn2 should be equal to rho s. So these are the boundary conditions that I have. So I need to solve my Laplace's equation subject to these boundary conditions. So let us do that. And when I do that, I will be able to ascertain the values of the constants a and b. So if I consider x is equal to d, therefore v is equal to 0 is equal to a1d plus b1. Therefore b1 is equal to minus a1d. Similarly, v2 is equal to 0 at B equal to 0, which gives me 0 plus is equal to 0 plus B2, which means from this equation 0 is equal to A to 0 plus B2. So B2 must also be 0. So I get B2 is equal to 0. Therefore, from this relation, I get an expression for V1 at x equal to A. At x equal to A, V1 is equal to A1 A plus B1. And from V2, I get that V2 is equal to A to A from epsilon 2. And these two quantities, V1 and V2, must be equal at x equal to A. Therefore, A1 A plus B1 is equal to A to A. Alright, now we know that D is equal to epsilon E is equal to minus epsilon grad V. And rho S is equal to dN1 minus dN2. What is dN1? Epsilon 1 of En1. And dN2 is equal to epsilon 2 En2, which gives me epsilon 1 dV1 dx plus epsilon 2 dV2 dx. En1 can be obtained from here by dV dx. So, epsilon 1 dV1 dx plus epsilon 2 dV2 dx is equal to minus epsilon 1 A1 plus epsilon 2 A2. Solving for A1, A2, I get the relations, the expressions for capital E1 and capital E2. Capital E1 is minus A1 and capital E2 is minus E2. So they are both constants. So E1 is a constant in material 1, E2 is a constant, but these are different constants. So this is how you solve for exact solution. Now the problem is that it is not always going to be possible to obtain the exact solution for for the Laplace's equation or Poisson's equation, especially when you have complicated geometries. And when you do not have an exact solution, you have to make do with approximate solutions, and these approximate solutions can be obtained by numerical techniques. Numerical techniques, we have a lot of computational resources available to us, and numerical techniques are very handy and frequently used for obtaining there are lots of commercial packages available for obtaining electrostatic field solutions within dielectrics. There are various kinds of numerical techniques available for solution of electrostatic fields. There is the finite difference method, the finite elements method, charge simulation method, method of images, among others. We are not going to discuss these numerical techniques, but here I will show you some of the field maps that we have obtained using a finite elements method for various electrode geometries. Now, depending upon the electrode geometry, that means the combination of conductors across which you place, one of which is the high voltage electrode and the other is the grounded electrode, and you have the dielectric in between. We have considered a dielectric of air. How does the field change? That has been illustrated here. We have used the finite element method to solve for the fields for different electrode geometries. As you can see, in the first case, you have a plane-plane arrangement. And because you have a plane-plane, the material is uniform in all cases. You have a uniform field, so you have a single value of the field in every region in space. And this could have been easily computed by E is equal to V by D. As long as your field is uniform, you don't need a gradient. E is simply V by D. Here you have a rod plane electrode. As you can see, the field is non-uniform. It is highest in the red region, and there is quite a bit of region where the field is high and it gradually falls off. Funnily, if you use a sphere-sphere gap, you do have a non-uniform field, in the sense the field is highest here and the field is lower in these regions, but in the gap distance where the sphere-sphere gap is closest to each other, the field is high, but the field is uniform. The field is more or less same value in this region. This is important, and we will use this finding later. The worst case scenario is when you have a needle plane electrode, you have a tip radius of very small tip radius, and you have a very small region. But in this small region, the field is very, very different from the rest of the electrode. You have a very high local field intensification. This is also something that is going to be of interest to us in the later lectures. So with this, we finish talking about electrostatic fields. And in the next topic that we will take up, we will talk about the various breakdown mechanisms in dielectric materials.